Okay, let's go ahead and get started. So, we've been talking a lot about probability lately. And probability, as we have been discussing, is not a statement of what will happen, but what could happen. And it also helps us a lot in statistics because we can use that information to determine things about our data. And I want to show us a new thing that we can do with it. Given that we have a normal distribution. So I've talked about normal distributions before. Okay, so if we have data and we graph its frequency, okay, continuous data might come out to be something like this, where we have all of these heights being the frequency of our data points. So the middle here would represent what? It actually represents three things. Okay, well, let's think about it for a second.
I emailed you the other day about the technique of some person.
Okay, I think that computer is open.
Which one?
The one right here?
This one?
Yeah. Okay, so let's think about it. Again, if this represents frequency, so down here where there's a really, really narrow bit of data, that means that these are data points that do not happen very often. Here, at this peak of this curve, this is data points that happen really, really, really often, or they're occurring quite a lot. So what would we call that? A data point that occurs more than any others? Mode, yeah. Okay, so in this normal distribution, the peak is the mode, but it's also two other things. Who remembers what? And what? The mean. Yeah, good. So this is the mode, the median, and the mean. Now, if this was skewed left or right, the highest point would still be the mode, but our median and mean would be kind of thrown off of that. They'd be pulled away on either side. Okay? But for today, we want to look at a normal distribution, one that is not skewed left or right, one that is perfectly distributed. Something we might see that's like this is height. So if we took the height of, I don't know, everybody on campus and distributed it like this, again, that would be continuous data because there's all sorts of different little data points that have varying amounts of decimals on them and things. It's continuous data. Most people would fall right around here at the mean, which would be somewhere between, I don't know, 5.5 to 6.5 feet. Okay? Now, some people are going to be shorter than that. Some people are going to be taller than that. Okay? Now, what we can do with this is we can actually get some probabilities out of this. So, if I wanted to know what's the probability that somebody might be, oh, I don't know, below 6 feet. Okay? Well, again, our mean is somewhere around 5 feet. 6 feet is just going to be right above that. So what I'm talking about is all of the data behind here. Again, if we want to know the probability of somebody being less than 6 feet tall, or equal to, let's say, it's going to be back this direction. All of this area right here represents all of that data. So how do we find that probability though? Well, we need what is called a z-score, or a standard score. I call it z-score, that's how I've always used the term, but you might hear this being called standard score. So this is calculated with just 3 numbers. Thank goodness, it's not one of those huge ones, right? Z equals x minus mu, the mean, divided by sigma, standard deviation. Okay, so what this does is it says, okay, what data point are we looking at? What data point do we want to know for less than or equal to? So again, the one that we're looking at right now in our heads is less than or equal to 6 feet. So that'd be our x, would be 6. Then the mean is whatever that mean is, whatever the average height is. So we take x minus that mean and then divide it by the standard deviation. Remember that standard deviation is a distance. It is a amount of distance from the mean. Okay? And we get standard deviation by saying it is sigma equals the square root of the sum of x minus the mean squared divided by n. So all of our x points minus our mean, square them all, and then add all those data points up, divide it by n, and take the square root. That's our standard deviation. Again, it is a distance. It tells us how far from the mean we are. So what we're doing here is we're finding x minus the mean, so how far it is from here to here, divided by that standard deviation, which is telling us a distance standard for our curve. And what this will give us is a number that represents the area back here. So let's put this into practice. Let's say we have some data values here. So the x we're looking at is again 6 feet. Okay? So we want to know everybody below or equal to 6 feet. So I'm going to say x is less than or equal to 6. Okay? And then we also need a mean. So we're going to say the mean is somewhere around, let's say 5.5, 5.5 feet. And then we need a standard deviation. Let's say that we don't have a lot of variance between our heights. Maybe something like 0.3. Okay, so 3/10 of a foot. Let's go ahead and plug it in, see what we get. So z equals, again, our x is 6, that's the one that we're looking at right now. That's just some data point that we're looking at in our total data, and we want to know what's the probability of being below that or equal to it, minus the mean, which in this case is 5.5, and then divide by our standard deviation, 0.3. Okay, so we just need to calculate this real quick. So 6 minus 5.5 is going to give us what? 0.5? Yeah, good. Okay. So now we have 0.5 divided by 0.3. So we'll just go ahead and divide that real quick, and we get 1.3 6 repeating. So it's just 6, 6, 6, 6, 6, 6, forever and ever and ever. Okay, now this number as it is right now is not very useful to us. Okay, there is another process of some formula and math that we got to do to kind of process this and get it into an actual probability. Thankfully, we don't need to do that at all because we have this. Okay, so in the real world, you would not calculate a probability from a z-score. What you would do is you would look it up on a z-table. Okay, so a z-table has our z-score, the first few digits of our z-score on this side, and the next digits of the z-score on this top here. And what we do is we look for the digits that we have in our z-score and line them up to find our probability. So all of the different probabilities are already calculated in this table. So let's see what we have here. Okay, first of all, this z-table calculates for areas below a particular point, which is exactly what we're doing. And this table is designed for positive z-values. Our z-value here is positive 1.6 repeating, so we need a positive z-table. There's another table that does the exact same thing just for negative values. Okay, so there's two tables we need. One for positive values, one for negative values, but they do the exact same thing. Okay, so let's see here. The first two digits of our z-score are 1.6, so we need to find 1.6. It's right there. And then the next digits are 0.6. So here. Okay? So now we need to line these things up. And there's our probability, 0.95154. Okay, so again, let's see, that was 95154. Okay. So that is the probability of somebody being less than 6 feet tall. Of course, we can put this into a percent form. So just move that decimal twice to the right, and we get 95.154% of people, at least in this theoretical thing, 95.154% of people are below 6 feet. Okay? So again, this z-score thing, along with the table, calculates the area behind a particular point. But that area represents a probability. So like we just saw here, we can use that probability to make some assumptions about our overall data. Like in this case, how many people, or what is the percent of people that are below 6 feet? Well, in this case, it's 95%. Does this make sense? Okay. Any questions? None? All right, let's try another one. I've got one here that I looked up earlier. If it will load. There we go. Okay. So we got a word problem here. It says the Acme Light Bulb Company has found that an average light bulb lasts for 1,000 hours with a standard deviation of 100 hours. Assume that the bulb life is normally distributed. Again, that means that it has a curve that is not skewed one way or the other. It's not got multiple modes, nothing like that. It's just this nice, gentle curve. Okay, what is the probability that a randomly selected light bulb will burn out in 1200 hours or less? Okay, so again, they've said that the average light bulb will burn out at 1,000 hours. So that's our mean. Okay. Now, the standard deviation of that is 100 hours. Whoops. Why can I not spell hours all of a sudden? I can tell you why. It's because dyslexia. Okay. And what we want to know is, what is the probability that if we just select a light bulb from, the assembly line, what's the probability that that thing will burn out in 1200 hours or less? So our X is less than or equal to 1200. Okay. So let's think about this on our curve real quick. Our mean is right here in the middle. That's 1,000 hours. What we're looking at, though, is 1,200 hours, which is above that mean, right? So the area that we're calculating here is all of this area back here. So, do we think there's going to be a very high probability that a bulb will burn out at 12,000 or below, or a low probability? Low? Anybody else got an answer? High? So some mixed answers here. Okay, well, let's go ahead and calculate this and see. Again, we're talking about the total area. So what's the probability that a bulb will fall into this area? All right. So again, z equals our x minus the mean over the standard deviation. So in this case, z equals 1,200 minus 1,000 all over 100. All right, well, what's 1,200 minus 1,000? 200, good. So z equals 200 over 100. All right, it's 200 divided by 100. 2, good. So z equals 2. Exactly 2 in this case, so I'm just going to put 0.200. I'm sorry, 2.00. Okay, positive z value, so we need our positive z table. And again, it is exactly 2. So looking at our positive z table here, first digit is 2, then next comes 0, so there's that, and there's our probability right there, 0.97725. All right. And so, of course, as a percent, we just move that decimal twice to the right, and we get 97.725%. So 97 almost 98% of light bulbs burn out either before or at 1200 hours. Does that make sense? Okay, so actually it's a very high probability that they will burn out before or at this point. And that's because since we're past that mean, we're actually dealing with quite a lot of area. Okay? So what about if we're below that mean? So I've got an example here that I made up for my previous class. Okay, so let's get our curve on here. So I just basically made up numbers for this one. I don't have any real world example for it. So we're saying that the mean for this set of data is 79. The standard deviation is 13. And the x that we're looking for is x is less than or equal to 54. So again, let's think about this on our curve. Our mean should be right here in the middle, splitting that data right in half. So half of our data is below the mean, half of our data is above the mean. Now, the x value that we're looking at is 54. That's below our mean. That's somewhere around here. So the area that we're looking at is this area here. So, do we think we're going to have a high probability of data points landing in this area or a low probability of data points landing in that area? Low. I would agree. And that's because, again, this area is so small. Okay. But just to make sure that we're right, let's go ahead and calculate this. So, z equals 54 minus 79 over 13. Okay. There's something I want to point out about this particular one. X is 54, mean or mu is 79, and we have to do x minus mu, 54 minus 79. What's that going to come out to be, positive or negative? Negative, obviously, yeah. So, at this point, we can immediately assume that we are going to need our negative z-table. Okay? So if you have an x that is less than your mean, pull out that negative z-table. If you have an x that is greater than your mean, pull out your positive z-table. All right. So let's go ahead and calculate this one. Let's see, 54 minus 79, that should be negative 25. Okay. And then we need to divide that by 13, so let's see what that is. 25, 13. We get negative 1.923. And there's a bunch of other decimals, but they're not useful in this point. Okay? So, again, we need our negative z-table because we have a negative z-score. It calculates the same thing. It calculates an area below a particular point. It's just that these are for negative values. So we have negative 1.9. So we need to find negative 1.9 here. There it is right there. And then the next digit is 2. So right here. So here's our probability. 0.02743. Okay? So what percent of data lies below that? Well, we just need to make this into a percent, move that decimal twice to the right, and we have about 2.7%. Which again makes sense. Like we said, this is a pretty small area. It's below the mean. Any questions? None? Okay. So something I want to point out. Both our positive z-table and our negative z-table calculate the same thing. They calculate the area behind a particular point. So this would be x is less than or equal to. This is also x is less than or equal to. They calculate area behind a point. So if that's what our z-tables do, how do we get above a point? Well, let's think about, again, what our curve represents. If we were to think about this as a percent, again, 50% of our data lies above the mean, right? 50% of our data lies below the mean. Well, altogether, what percent is that? 100%, yeah. That's 100% of our data. What is 100, not as a percent, but converted into a decimal? In other words, what would the probability be if we had 100% and we wanted to convert it back into a probability? Good. So again, the whole curve represents 100%, but as a probability, that would be 1. Okay, well, we just calculated this area right here. And we found that its probability is 0.02743. So we don't want that this time. We want the stuff that's above this point. We want that. So does anybody have any ideas about how we would get there? Excellent, good. Since this whole thing is 1, if we just want to know this part, then we could subtract, literally subtract this part from it and get it. Well, we know what this part is. It's 0.02743. If we subtract that from 1, it will take this off and just leave us with this part. Does that make sense? Good. Okay, so let's go ahead and figure that out. So instead, let's do x is greater than or equal to 54. All we got to do is do 1 minus 0.02743, and that gives us a probability of 0.97257. Or, of course, as a percent, that would be 97.257%. So 2.7% of our data lies in this area. 97% of it lies in this area. Does that make sense? Okay. So maybe instead of wanting to know if a light bulb will burn out before 1200 hours, maybe we want to know what's the probability that it'll burn out after 1200 hours. Well, we've already gotten our z-score and our probability. We just need to subtract this from 1, right? Okay. So 1 minus, let's see, 0.97725. So here, the probability of a light bulb burning out after that point would be 0.02275, or as a percent, 2.3% if I round it. So not a great probability. But it's that easy. Any questions? Okay. Now, these tables, you can find them online. All you got to do is look up z-table. Okay? And you might see some that don't calculate below, but instead calculate above. All they have done, though, is take this number and subtract it from 1, flip the table. Okay? So do you need 4 different tables? Do you need one to calculate below, one to calculate above, one to calculate positive, one to calculate negative? No, that's too many tables. Just get yourself these two. The positive table and the negative table for calculating below below an x. And then if you need to calculate above that x, just subtract your number from 1. Any questions? None? Okay, good. What is today, Wednesday? So Friday's the next class? Yeah. Friday we'll be getting into something a little bit more interesting than that, I think. We know how to calculate above, and we know how to calculate below. What about if we want to calculate between? Okay, so that's what we're going to be learning on Friday. So I hope you have a good day, and I will see y'all on Friday. Thank you. Oh, and in the future, just make sure that you sit at that desk when you come in. Okay? Hmm?
Oh my goodness.
The wife's giving you difficulty?
Oh, it's, well, I mean, we couldn't never have difficulty.
Oh.